So hello everyone, welcome you all at Lokesh Sir Unlimited Studies. So student, we starting in today's classes a reflecting type of telescope. So make a heading reflecting type of telescope. So by the name here the word reflecting is used. It means some mirror will be there. Okay. And what is the use of the mirror? We have already developed the telescope, that is a refracting type of telescope, yesterday in a form of uh, what telescope yesterday we have derived? This one, astronomical telescope. Clear? Astronomical telescope. Now, what is problem with the use of astronomical telescope? Yes, so the problem related to the lens or refracting medium is called aberrations. Okay, so there are too many types of aberrations are there. Okay, student. So see what is problem faced during the use of um, a telescope that is made up of lens. You know, student, we have a lens and formula for lens maker's formula 1 upon f equals to 1 mu 2 minus 1, 1 upon r1 minus 1 upon r2. Okay, this is the formula for lens maker's formula. Okay, and this formula is used to make a lens. Now, mu is inversely proportional to lambda. Clear? We know mu is inversely proportional to V and V is proportional to lambda. So mu is inversely proportional to lambda. Clear? Means for the different color, and lambda refers to the color. Okay. And you know white light having 7 colors. A white light made up of 7 colors. Clear or not clear? So there are 7 type of colors with a name of a spectrum Wibgyor. Okay. So 7 colors are there and 7 color having their respectively 7 wavelengths. For red color, there is a wavelength of red, lambda red. Clear? And for a lambda red, as it is very high, so mu refractive index for the red color will be very less. So mu red, okay, mu red, refractive index of the red color is very small. So for a white light, this lens will focus the different color in the different position. Yes or no? Because the refractive index is different, so the focal length for the individual colors will also different. So instead of getting an intense image at a single point, you getting a band of the colors. Okay, band of color. And there is not definite boundary. So this fault, this problem is called chromatic aberrations. Okay, chromatic aberrations. So this can be removed with the help of a mirror. Why? Because in mirror, the focal length 1 upon f equals to 1 upon v minus 1 upon u. You see, student, there is no term related to the refractive index of the medium. Yes or no? So as the focal length is independent from the refractive index, focal length is independent from the refractive index means it is independent from the wavelength, and you will have a sharp image that is free from the chromatic aberrations. Clear? So that's why we are going to use here a mirror in the place of a lens. Okay. So what is reflecting type of telescope? This is called Cassegrainian telescope. It is an important over the refracting type of telescope. Yes, yesterday we have studied the telescope, that is astronomical telescope, that is the example of refracting type of telescope. Okay. Now, objective lens is replaced by a concave parabolic mirror of large aperture. Yes. So here the objective lens is replaced by a concave parabolic objective mirror. So in the case of place of objective lens, there is a objective mirror. Okay. This is the your objective mirror. This is your objective mirror. So objective lens is replaced by a concave parabolic mirror of the large aperture, which is free from the chromatic and spherical aberrations. So there are two losses in the lens. One is called chromatic aberration and second is called spherical aberration. So this is free from the chromatic and spherical aberrations. Okay. So this is the objective mirror. So this diagram is important. Then after the image form is much brighter and the reflecting type of telescope has much higher resolving power to the refracting type of telescope. So two advantages are here. The image is the image formed is much brighter. Why it is much brighter? Because the aperture is very large enough here. Okay, so enough amount of light entering here. So on the objective mirror, so you will have a fine brighter image. First thing, you will have the image formed is much brighter and the reflecting type of telescope has much higher resolving power. Resolving power is also much high, means if there are two lines, so you can have better contrast and you can resolve these two lines very clearly. Okay, as chromatic aberrations is not present there, that is why. Much higher resolving power compared to the refracting type of telescope. Such a telescope is known as Cassegrainian telescope. Okay, on the name of its inventor. A reflecting type of telescope was designed initially by Newton and modified by Cassegrainian. So make this diagram. This is the diagram important. Okay, for examination point of view. Now check the working here. First rays are coming parallel on the objective mirror. Now they reflected on this convex type of mirror, that is secondary mirror. So this is convex. Now the rays from the infinite source, they are meet at a point, okay, in the eyepiece. Okay, this is eyepiece. Clear? Indeed, in the diagram, C is the capital C. C is the parabolic concave mirror. So this I'm talking about this. Capital C is the parabolic concave reflector about 200-inch aperture. Yes, 200-inch aperture with a narrow hole at the center. Yes, with a narrow hole at the center. So here parallel rays from a distant star entering in the telescope in a direction parallel to the principal axis of the mirror tend to collect at the focus of the mirror. Yes, definitely. So they are tending to collect at the focus of the mirror because you know the parallel beams of light after the reflection will get collected at their focus. So they are try to collected at the focus and the focus will be lying somewhere here. Okay, but a convex mirror is placed there in between the path of the rays. Parallel rays from a distant star entering in the telescope in a direction parallel to the principal axis of the mirror tend to collect at the focus of the mirror. But these reflected rays encounter secondary convex mirror B. Yes, the name of mirror B is called secondary convex mirror. Secondary convex mirror B, before meeting at the focus, the convex mirror reflects them into the eyepiece and the final image is seen through the eyepiece. The final image as seen by the eyepiece is inverted with respect to the object because we are using a mirror here and we finding here the real image of the object. So the real image will be inverted with respect to the object. Clear? Hmm. In normal adjustment, magnifying power of a reflecting telescope is given by FO upon FE. Yes, M is equals to FO upon FE. So FO is the mirror. So mirror equals, we have the same formula for normal adjustment means when your final image is formed at a normal adjustment. Okay. So when your object is kept on infinity, so you have final image FO is equals to R by 2. We have the formula for mirror F equals to R by 2. So you have F equal to R by 2 upon FE. So this is only formula M equals to, where R is the radius of curvature for the concave reflector. Yes, the bigger mirror is equals to concave reflector. So R is the radius of curvature for the concave reflector and FE is the focal length for eyepiece. Next type of telescope is Newtonian reflecting type of telescope. The parallel beam of light coming from the distant star is reflected by the large parabolic concave reflector C to the plane mirror. Yes. So here the large from the large star, okay, the parallel beam from the light coming from a distant stars reflected by the large parabolic mirror. So here we have a large parabolic mirror. The rays parallel coming rays from a distant star get incidented on the mirror and they are reflected at some point, obviously on the focus of this parabolic reflector, concave reflector. See, to a plane mirror. Now there is a plane mirror. Okay. Now after striking a plane mirror, these rays get bends using the principle of reflection. Okay. To a plane mirror M. This mirror is inclined at an angle of 45-degree to the axis of C. Yes. So this is the axis of C, and this plane mirror is inclined with the angle of 45 degrees. So this angle is equals to how much? 45-degree. Hmm. To the axis of C. The plane mirror reflects the beam forming a real image I in front of eyepiece. So this mirror is reflecting the rays gathered from the parabolic reflector and make a image E on the eyepiece. Okay. Plane mirror reflect the beam forming a real image I in front of an eyepiece. Eyepiece is a simple magnifier lens that is used to magnify the final image. The eyepiece act as a magnifier and the forms and the final virtual and magnified image of the star is seen distinctly by the eye. Yes. So this is used to magnify. Simple, it is a magnifying glass. So it is used to magnify the image of object I. Now, talking about the advantages of this reflecting type of telescope. As I said first, there is no chromatic and no spherical aberrations due to the use of mirror objective in the place of lenses. Image is brighter as compared to the refracting type of telescope. For both the Cassegrainian and Newtonian reflecting type of telescope, okay, the image will be bright. Remember, the first Newtonian telescope was discovered. Okay, then after in the same telescope discovered by the Newton, Cassegrainian has made some changes and he produces this type of telescope. Clear or not clear? Hmm. So second image is brighter as compared to the refracting type of telescope, and high resolution is achieved by using a mirror of larger aperture. So as larger aperture collect more and more of the light, okay, so this wide aperture is enough to gather a high amount of light and you will have a brighter image. Clear? So a small telescope has an objective lens of focal length 150 centimeter. So you have given a 150 centimeter, a small telescope. So this is the focal length of objective lens. FO becomes equals to 150 centimeter. Clear? And an eyepiece of the focal length 5 centimeter. So FE is equals to 5 centimeter. Very small. If this telescope is used to view an 100-meter high tower 3 kilometer away. Yes. So what is this? This is height of object. 100-meter high tower. This is height of object. HO equals to 100 meter. Clear? 100-meter high object and tower 3 kilometer high, 3 kilometer away. This means the distance of the tower from the objective lens is equals to 3 kilometer. Okay. Find the height of the final image. So you have to find the height of the image. You have to find h dash or hi. So by using the formula, magnification is equals to hi upon ho. So you have to use finally the magnification. But before that, find the height of the final image when it is formed as 25 centimeter away from the eyepiece. Means the case is valid when your final image is formed at LDDV. Yes. Clear? Maximum magnification case is there. So first write FO, focal length of the objective lens. For objective lens is convex, so it will be positive. FE will be positive, and D equals to 25 centimeter. Apply the formula for magnification. M equals to minus FO upon FE, 1 plus FE by D. So you got minus 36. Clear or not clear? Okay. Let the height of the final image is equals to how much? H centimeter. So 10 beta is equals to h upon 25. Height of the final image is equals to h centimeter. We don't know what is the height of final image. Clear? Yes, this was the eyepiece. Yesterday we have seen, and this was the angle made by the eyepiece. This is final image. H dash is the final image, right? And your final image is formed at a distance of um, d. So tan beta is equals to perpendicular upon base. So perpendicular becomes h and distance become d, and this is equals to 25 centimeter. Clear or not clear? And this angle was beta. Yesterday we have taken this one as beta. Clear or not clear? Beta is the visual angle made by the image, by the final image at I. Okay, kept at LDDV. Clear or not clear? Now, this becomes 10 beta. Now, 10 alpha. 10 alpha equals to perpendicular upon base. See here, perpendicular upon base for alpha. You having a tower of height, how much? 100 meter. And it is distant 3 kilometer, right? So, tan theta is equals to perpendicular upon base. It is equals to 100 upon 3000. Now, two zeros get cancelled and it will become 1 upon 30. So, alpha is equals to visual angle subtended by the object at objective. Clear? So, by this, find minus 36 m is equals to 10 beta upon 10 alpha. Place these values here and you will have h equals to minus 30 centimeter. Negative sign will give indicates you the inverted image. Okay, noted.